Okay, I'd like to share with you a little bit of work I've been doing in a 9-axis or 9 degree of freedom inertial measurement system, and to step you through some of the progress I've made and some of the issues I'm still having. As far as the hardware that I'm using, it's based on a Arduino microcontroller. On top of the Arduino, I have a shield that is connected to a radio so that I can send the data to and from the computer through this little XV radio. As far as the inertial measurement unit itself, I am using a 3-axis accelerometer from Adafruit, the LSM303DLHC. And then that has a 3-axis acceleration and also a 3-axis magnetometer. And then I'm also using the L3G020 3-axis gyro from Adafruit. With these two chips, I get the full 9 degree of freedom. While I'm showing these, actually, if you're just getting started with inertial measurement and want to play around with an accelerometer, I really recommend a 3-axis accelerometer from Vpython. It's a very simple chip. You can get it up and running with about 5 to 10 lines of code, very simple digital read, and it's the easiest way to start playing around with these. These are on the I2C bus. There's some advantages of that, but it also slows you down a little bit if you're just getting started. So let me go ahead and show you some of the results right now, and I'll start kind of with the simplest thing, which is just the accelerometer. And I'm just going to show you the raw signals coming off the x-axis, y-axis, and z-axis acceleration. And what you can see is the pink is the x-axis, the green is the y-axis, and the blue is the z-axis. And these things are really easy to get going, and you can see that you just get data streaming off this thing very nicely. And if you start playing around with it, for instance, if I go like this, you can see that that is the x-axis, which is pink, and you can see that I get a nice big acceleration signal as I move the device. Now you might see a little bit of noise in the other two axes. Come to find out, these chips have very good cross-axis isolation, but it's just as I'm playing with it, it's hard for me to move it precisely in the x-axis. And so if you see noise on one of the other axis signals, that's more how I'm moving it and not a fundamental limitation of the chip. If I could align it better, I could do better. But you can see we've got x-axis, and then in green we have y-axis, and you can see it's working well, and then the z-axis in blue up top is like this. Okay, so you play around with these a little bit and you start getting real excited about how easy it is to get this fairly nice acceleration data. And the first thing that you start thinking is, wow, if I integrate acceleration twice, I can get position, and I could actually start measuring position of things with these. Well, you can try doing that. But real quickly, what you find is integration works much better in calculus class than it does when you're working with microcontrollers and sensors. And what you find is the noise in the signal, by the time you integrate this twice, your system has such enormous drift that is pretty much completely useless. And so it is an accelerometer, it's a great accelerometer, but it's not good for measuring position. So you play around with it a little bit more, and what you see is, if you watch the z-axis, this is just the raw data coming off the accelerometer. If I turn it upside down, I get a very large change in signal. And similarly, I can tilt the y-axis, green is up, now green is down, or the x-axis, the pink is up, and now the pink is down. And what you start seeing is that it might not be very good for measuring position, but you can kind of start seeing that you're getting something that looks like it might be just a really nice tilt sensor. I'm going to turn the other axes off and just look at the z-axis. And what you can see is that you can start very nicely looking at tilt. Okay? And right now I'm just looking at the raw signals coming off the accelerometer. What you want to do is kind of calibrate this. This would be, if it's sitting perfectly still with the z-axis pointed up, that should correspond to 1G. And then if I turn it down, that signal should correspond to negative 1G. So I can take my two raw readings and I can map those between 1 and minus 1G, and I can actually get a calibrated signal fairly easy. And so let me turn on my calibrated signals, x-axis, y-axis, and z-axis accelerometer. And now you can see up here I have plus 1G, minus 1G. On the y-axis, plus 1G, minus 1G, And then finally on the x-axis in blue, plus 1g, minus 1g. And so I've got this very carefully calibrated and very accurately measuring that vertical vector due to the force of gravity. Well, actually, if I look at this, let me just look at a couple of axes. Let me look at the y and z. And if I try to spin this very carefully, what you can start seeing is that I should have done probably x and z. Okay? So if I spin it like this very carefully, and if the smoother I could spin it, the better you could see it, that by spinning it at a constant rate, it looks like that we're pretty much getting a sine and a cosine wave. And that sort of is a clue. If you go in and actually do the trigonometry, you can see that you can get a fairly accurate angle of tilt if you just do the arc sine. Now, if you take into account all the three-dimensional effects, the tilt angle, and if you're tilting along two axes, is a little bit more complicated than that. But the simple equation is just take the arc sine of the acceleration signal, and that's a pretty darn good indication of the tilt. And so what you can see in doing that is that you can get a very nice and accurate measure of tilt using an accelerometer. Now, you play around with that a little bit and you get real excited because you can very accurately measure that tilt just using a 3-axis accelerometer. But what you end up doing is you start thinking that you have a tilt meter. One day while you're tilting it, you shake it a little bit and you're reminded that these are not tilt meters, they are in fact accelerometers. And they're tilt meters only if you're very smoothly tilting, but if you have any other type of motion on there, you get large errors in that tilt because of the acceleration signal that you have in addition to just the 1g vector that you get from gravity. Okay, so you sort of were excited there for a little while, but then you kind of got hung, and then you realize that there's really something better to measure tilt than accelerometer, and that's a gyro. And basically a gyro measures angular velocity. The nice thing about that is if you want to get from velocity to angle, you just have to do one integration, and that can be maybe a little bit more tractable. And also, the gyros have fairly low noise. And so let's just look at this x-axis gyro. I'll turn it on. And it's from the other chip. This is auto-scaling, and so when it doesn't get a signal a little while, it just amplifies the noise. And so actually this is a very clean signal. And I can show that by basically what I'm going to do is I'm going to rotate in the x-axis. And you can see that if you look carefully and think about it, that this is measuring angular velocity, because when I'm still, it goes back to 0. And what you're looking at is you're looking at the angular velocity as I'm moving it. But you can see that it actually works pretty well. And if I look at all three axes, x, gyro, y-axis, and z-axis, you can see if I move along y, you see a signal in the green. If I move along x, you see a signal in the red. And then if I move it around z, you see a nice signal in the blue. So I can measure angular velocity in all three directions, or around all three axes. So with that, why don't we give it a try and see if we can measure our rotational position by integrating these gyro signals. And so I'll take these raw data and numerically integrate them. And I can show that here and show the integrated signal where I integrate the angular velocity into an angle. And then you can see I get three nice signals. And if I move like this or move like this, you can see that I'm getting a signal. Let me just put one so you can see it a little bit more clearly. Let's see, yeah, that's the X. And you see now it actually measures the position. It's not measuring velocity, it's measuring the tilt. Okay, very nice. I can turn that off and turn the Y on. You can see I get a Y signal. And look how nice and smooth that data is. One of the issues with the accelerometer was the amount of noise in it. And you can see that the gyro doesn't have noise. It's got a very clean signal and almost no noise. Now that's the good news. What the bad news is you're starting to see here. Okay, even though there's not noise, there's drift. And what you can see is if I just set it down and leave it at a very fixed angle, I have this rather significant drift. And probably within a few minutes, you could get a couple hundred degrees of drift. And then something will happen, like right there, it picked up a little bit of a signal, and now it's a little bit like off to the races on drift. Notice that it's still got a real clean signal on the change, but you just have this overwhelming background drift problem. So you can see kind of what you're up against here is that you love the accelerometer because there is no drift in the accelerometer at all. But the accelerometer is noisy, which makes it difficult to integrate. And besides being noisy, it also is an accelerometer, and therefore if you're trying to use it for tilt and you get some vibration, that is a mess. So if you think about it, what you would like is you would like to sort of get your steady state value from the accelerometer because there's no drift. So in steady state conditions, you want to kind of trust that reading from the accelerometer, but under a changing signal, you want to trust the changing signal of the gyro because the gyro is not sensitive to acceleration. When you see a changing signal on the gyro, you know that it's a real signal. But you can sort of track where you should be, that baseline number you should get from the acceleration. And so basically you can do some math where you're integrating the values coming off the accelerometers and the gyros, and you're weighting the value of the accelerometer to give you a stable baseline value. And then you're weighting the change signal more coming off of the gyro. And so by fusing these two data streams between the accelerometer and the gyro, you can actually get a very accurate signal. Now the nice thing is that I have an x-axis accelerometer and rotation about the x-axis. I have a y-axis accelerometer and rotation around the y-axis. The challenge is that with the accelerometer, with the gyro, if I look at this other signal, the nice thing is with the gyro, I can see this rotation that is parallel to the Earth. The problem is the accelerometer cannot see this one because the gravity vector is coming straight down. And so I can compensate the other two axes with the x accelerometer and the x gyro gives me one axis. The y acceleration and the y gyro give me another axis. Those work well, but I don't have an accelerometer that I can pair up with this z-axis gyro, and so I've sort of got a problem because I would still have drift in the z-axis. But what you can do is, remember this first chip actually has a 3-axis magnetometer, and I have this vector that's coming of the magnetic field of the Earth, and that gives me a signal that I can fuse with the gyro signal. And by doing that, there's no drift in the magnetometer because north is north. That vector is very stable, and the sensor is very stable, but I can use that for that other sensor in place of the accelerometer. So basically I end up using the 3-axis of magnetometer, the 3-axis of acceleration, and the 3-axis of gyro. And when I do that, what I can end up with is a measurement of roll and pitch and heading. And these are those data that are coming from the fusion between these nine axes. And let's see here, it looks like this would be the roll, and it looks like the roll is here. Let's see if I get this right. Yeah, okay. And what you can see is that I can very accurately measure this roll. Okay. And I have one that is a little bit of a cleaner signal where we've got the gyros helping out a little bit more. And let's look at this, okay? So that is the pitch. You can see a very nice signal on the pitch. And what I want you to see is that now that I've combined the accelerometer and the gyro, that you've got something that if I just put it there, that is not drifting. The other thing that you see is that there's virtually no noise in the data. So by fusing that accelerometer and the gyro, I'm able to have the best of both worlds and to not have drift and to not have noise either. And so that's just very, very nice. And so that is the pitch. Now let's turn on the roll. Okay. Let's look here at the roll. So that would be there and there. And see, just real nice. I can kind of go in small steps. You can see how well it tracks my motion and how cleanly the signal is looking. Okay, and now let's look at roll and pitch together. Okay, so you can see if I roll, my pitch is staying steady. This is my pitch. If I change the pitch, my roll is staying constant. And then if I change my roll, my pitch is well behaved. And both of these signals are real clean. Now the yaw is the one like this, and so if I turn the yaw on, again the yaw is the magnetometer combined with the gyro, and that one you're looking at in the purple. You can see I'm pointing north, east, south, and there's a place that it jumps from positive 180 to minus 180, so you have that discontinuity as you're going around the 360 degrees. But you can see really nice left and right, yaw, really nice pitch, and really nice roll. And the nice thing is that you can do this and the axes are well behaved. You can tilt, roll, and pitch, or you can do the yaw, and it all works very, very well together. And so that is basically how I've combined the roll, the pitch, and the yaw, created from a 3-axis accelerometer, a 3-axis gyro, and a 3-axis magnetometer. But what I want to show you is that things get really fun now if you start taking that and start trying to more accurately or more precisely use it as an indication of your actual position. And let me see, I have to upload a different program, and so it'll take me just a second here. I got to kill a few of these windows, and then I have to call up my Arduino, and we're going to load a different program. And let's see, sometimes it's a little tricky to do this with the radio on it, but if I have my jumpers in the right position, I might just be able to do it. Wrong serial port. Try again. Okay. But what I'm doing is you want to actually take this data to a real program, and so the program that I'm going to be taking it to is a very nice program which is called Vpython. And Vpython has some very powerful graphics capabilities, and it's fairly easy to get the data in over the C port, over the serial port. A lot of people really like C. C is a hard program to learn to program in, and I'm not very good at C. And Python is a little bit easier and a little bit more, Python is a little easier to learn and a little bit more intuitive. Those of us who learned on basic, Python is a lot more like basic. So anyway, let me take this and fire up this program, and let me see if I can. I'm going to need to move these jumpers back to turn the radio back on. No matter what you do, these jumpers are always in the wrong spot. Okay, and let me close that, and let's try this again. Okay, so we're going to run it. We've got the jumpers in the right spot. And check out these windows. I probably just need to kill it and try it again. And we will run. these radios really don't like going from being programmed to communicating. So what you can see here is that I've got a model of my circuit, and that model is responding to my hand motion. Okay, so I'll tilt it towards you. You can see the XB radio, you can see the interface, you can see the Arduino symbol. I can rotate it around. Bring it back this way. You can see we even got the red blinking light. And so let's look at, this would be pitch up and pitch down. You can see that it's smooth. We can roll left, roll right. You can see underneath it. We can look at the yaw. I got in a little trouble area there, but let's try it this way. Okay. You can see the gyro chip and the accelerometer chip there. And so let's go up and down and up, left, right, quickly. Okay. Turn it around this way, that way, and that way. And so basically this is working really well all the way around. And it's very responsive and it's very accurate. Notice if I hold it still, my hand is twitching a little bit. Like if I set it down, okay, you see it stabilizes. There's just no drift at all in that, and there's really not very much noise at all. Very, very stable when it's sitting still, and then it just tracks my motion very well. Now, let's talk about where my problem areas are that I am still working on. Remember, I'm doing this filter and fusing of data between, for this, it's between the magnetometer and the gyro. And so basically what happens is when I get to this positive 180 degrees and I move it a little bit further, it's got to jump to negative 180 degrees. Well, the problem is that when you get that large change, the filter thinks it's noise and wants to filter it out. So rather than just popping over, it rotates the other way. And if I turn the filter off, it'll make this transition from here to here without doing that. But then I get more jitter all the way around. And so I need to figure out a way to turn that filter off to go smoothly from the positive 180 to just a degree over, or positive 179 to minus 179, and have it make that transition a little bit more smoothly. So that's a problem I still have to work on. Now another one, and this is a general problem with Euler angles, is that I come up here, when I get absolutely vertical, the yaw doesn't have any meaning anymore, and so the thing just kind of starts wandering around, and it's kind of like a singularity. It's equivalent, it's the mathematical equivalent of gimbal lock in a physical system, and so it doesn't really work at these singularity points. I probably need to go in and see if I can put some special cases in, but the same thing happens here. Sometimes it'll flip around at these various 90-degree points, although it seems to kind of be behaving there. Okay, so it doesn't work at the 90-degree points, and also it doesn't work upside down. And this is all the kind of ambiguity with the arc trig functions, that if you look, I come up here, and if I tilt it past 90 degrees, it starts coming back the other way because of that ambiguity in the arc trig functions. And so I need to try to see if I can do some special cases for that a little bit better. But you can see here that as far as any position an airplane would be in, this is working very great. Also, if you made it smaller, use a PC board and some stuff that you could very accurately track your hand position. Basically, if you were trying to do a hand or a head tracker, it would work very well. So anyway, that's where I am now. I'm hoping in the next few weeks to work out some of these bugs and to have something even better to show you. Thanks a lot.